So in this class, we will do two concepts of multivariable random variables. One is called correlation and covariance. So we'll assume that x and y are two random variables, two continuous random variables. Right, with let's say joint density f of xy. So with joint density f of xy from R2 to R plus. So that's given to us. Then covariance essentially tells you how the two random variables are related to each other. It specifies some amount of relationship or quantifies it in terms of one number. So we'll try and understand that number a little bit. So then the first definition is the covariance of xy is given by, so you write it as COV in bracket x comma y, and as we've seen the discrete setup, it's the same as just expected value of x minus ex times y minus ey. Right. Now how do you compute some expression like this? So you know that this is a function of x and y, and then these two are certain numbers, right? And all you have to do is just integrate this functional with regard to joint density. So first, before, let me just let's clarify a couple of things before we proceed. Let's assume that ex is finite and ey also is finite. Yes, let's assume both these things are finite, and we're trying to compute the covariance of x comma y. So that's equal to now what? Now it's equal to, like you said, integral minus infinity to infinity on the y variable, let's say, and then on the x variable. So you have a dx and a dy. Right? And what do you do inside? You just put x minus ex, which is a constant, and y, little y, minus ey, which is ey is another constant. So I'm running out of space here, so I just move it across. Right? And then I will put the density f of x comma y. Right? And like before, we know how to do this, so we'll keep the inside integral in terms of constant in terms of y. So let me color y a little differently. Let me just color this guy as, let's say, pink, let's say. So all the y becomes pink. So the inside integral, everybody is a constant. So let's say all the constants, I'll mark it as y, or let's say I'll keep y as constant, let's say. And I'll keep this integral as pink. So the inside integral is an integral with regard to x only, and you keep y constant. So maybe I should just move this across to the outside this guy. So this is called the covariance. Of course, it's a measure of dependence. So for example, like suppose, how do you understand this? Like before, if x is larger than ex and at the same time y is larger than ey, then this integral is going to be large, right? And if x is smaller than ex and y is also smaller than ex, then also it will be large. That means x and y are very dependent in some sense. So if x and y are independent, it doesn't really matter, then you should expect this covariance to go away. It should be 0. So let's try and see if all those things, all those intuition matrices. So first thing is let's try and see independence first. Let's try and see. Let's try and do a simple one. So what's covariance xy? So now one thing you notice that from this setup, so covariance of xy. So let's do first property. Covariance of x comma y is the same as this person right here, right? It's the same as this person right here. Right. So that's just I'm just cutting and pasting there. There's no problem, right? So now what I can do is I can always swap the integrals and swap the order of the two terms, right? So what I can do is, let me just do it for you. So let me just put this in here. Let me copy it. Let me place it first inside. Let me place the white integral outside. I can do this because everything is non-negative, and of course there's an integrability condition involved in terms of how you can flip it, but let's assume you can flip it for the time being. So modulo that mathematical technicality, if I can flip the two integrals, so I have minus infinity to infinity, and I have inside, I have this guy is white here, and inside I have minus infinity to infinity. Then here I put the y first, so I put the y first, copy, put the y first, and then I put the x next. Okay. And then I put f of xy, right? So f of xy, and then I integrate out the y first, and then the x next. Yeah. Now, if you observe, this is the same as everything is the same except I've done the y first and the x next. So if I go back up here and I copy this whole thing down, so I bring it down here, this is exactly this. So now here what I do is I just flip this across. I move it across here and I move it across here. So I've just flipped the products. So that means the covariance of xy is same as covariance of yx. So covariance is symmetric, right? So let me copy this down. Very cool. So there's really it's a sort of a nice way of understanding it. Actually, I needn't have done this couple of flips here. I could have just done from here to here directly to show this. I just did just to show the. You'll be a little careful when it's auto integration, but I didn't have to do that also. I could have just started from here and just come directly here. Start from here, come directly here, and then say this. Very good. So covariance is a symmetric function of x and y. That's the first thing. The second thing also, which is also sort of it comes from the variance calculation that we've already seen. So you look at the covariance of x comma y, right? So that's just going to be equal to, let me just go back here and let me paste it. It's just this person right here, right? This person right here. Now that's going to be equal to, if I do the algebra inside, the expectation, so I get xy, I get x times ey, right? And I get minus y times ex, and I get plus ex times ey. Okay, that's what we do. Now, this whole thing is going to be, you do the algebra properly, correctly, it's a simple exercise. It will reduce to, if you use linearity expectation, what happens now, and these two are constants, right? This is a constant, this is a constant, these are constants, right? These are constants. So let me just mark them down. They're constants. So what will happen, you will get, first term is exy, that's the first term, right? The second term is just going to be ex times ey, because the ey term is a constant. The third term is ey times ex, and the last one is ex times ey. Okay, so then if you do this, what will happen, you have your one term cancelling off with this person right here, so you'll have to write this off. So therefore the covariance of xy is the same as exy minus ex times ey. That's nice to see that, right? That's very nice to see. Very cool. So then the other things are kind of, I'll leave as exercises. One can check this. It's not a problem. That it's easy to check. Let me leave this facts as exercises that you can easily work it out. It's not that hard. You can check that if you look at the covariance of x and x itself, there is a, so y is equal to x, right? So then this is going to be equal to just the variance of x. That's kind of obvious, right, from the formula. If you go to the formula right here, covariance of xy is just going to be e of x times x minus e of x times y times, if y is equal to x, I get this whole squared, and that's just variance of x. So maybe I'll just write this down like this. Okay, I'll leave it. Okay, maybe equal to, from this step, if I come down, I'll get e of x squared minus e of x the whole square, right? Because I know covariance of xy is just this person, and then I get this, and that's equal to variance of x. So there's no real difference there. So then next thing you can try and do is the following. You can try and see if this interesting fact, if of linearity you can check, but I'll let you check that. So if you have covariance of x and then ay plus b, what will that be? So that'll, you have to just, it's bilinear, so it'd be a times covariance of x comma y plus you'll have b times so b times z, let's say b times z, so you'll have plus b times covariance of x comma z, right? That's what you have. Very nice. There's some properties you can show. Of course, assuming that all the covariances exist and they're all well defined, and you can add them up. Okay, so let me go back to this formula 1 and see something extra I can develop in this, right? So let's say we have two independent random variables. Okay? So let's say x and y are independent. Suppose I'm given that fact to you. Independent random variables. So here what happens now? Here one should try to see. So now let's see. So now first thing you know is that the joint density of f of x comma y is going to split up as a product of fxy times fyy, right? For all x and y, and this is a fact we know, right? Where these two are the marginal densities, right? Correct. Now what I do is I observe the following. Now if you look at e of xy, so I'm trying to understand what the covariance will be, right? So first step is I'll understand what exy is. Exy we know is minus infinity. Let's do the y for the pink. So I'll have y, and I have an x, and I have a fxx, so x will be x, sorry, and fyy, right? And then dy dx, right? dy and then dx. But now if you observe in the pink part, this x fx doesn't at all worry about the integrand of dy, so I can pull it out. So it's going to be equal to, so I pull this out, I pull the x fx out, pull it out, I move this back inside, pull it back inside. This is what I'll get if I pull the x integral outside, right? This is what I'll get, because these two don't depend on the inside integral. The pink integral doesn't depend on x, it only depends on y, right? Now this entire sort of pink integral doesn't depend on x at all, right? So let me just do a little bit of coloring thing. So let me call everything as pink. Okay. Very good. So the pink integral doesn't depend on, I can pull the whole thing outside. So what I'll do is I'll take this guy, right? I'll move it outside, I'll copy it, I'll move it outside. And what I'm left inside is just this white guy. Just this white guy. Right, that's what I'm left with. This times is equal to this times dx. But what is this now? This is the same as the first person is ey, the second person is ex. So exy is same as ey times ex, or the same as ex times ey. So what have we shown? If x and y are independent on a variable, this implies this, which implies that exy is ex times ey. But now covariance is just exy minus ex times ey. So let me copy this down. Covariance, sorry, copy this down. Covariance of xy implies covariance of xy is equal to this person right here from 1. Exactly this guy. So I'll have a pink arrow coming in, but we'll remove that pink arrow. So this implies equal to this, and let me call this equation 2. So by equation 2 I know exy is ex times ey. So by equation 2 I can get this to be equal to 0. So it's a very important fact. That is, the covariance is, if x and y are independent, then the covariance is 0. It's kind of a nice fact to keep in mind. But it's important to understand the reverse is not true. So let's try and see. Suppose I have the covariance is 0. Does it imply independence? Right. So let's just check that. So I'll let you think a little bit for a second to see if you can think of an example where. So here what I have shown. Here I've shown if x and y are two independent random variables, then the covariance is 0. Right. That's what I've shown here. So now I just want you to think a little bit. If x and y are not independent, can you find an example for which the covariance will remain 0? Okay, so let me do that. So we go over here. So let's assume. So let's do an example. I'll do an example. So it's not true. So I'll do an example. That is, you can have two random variables who are dependent clearly. So let's do that. Let me write the examples down. So let's say y. Let's say x is, let's say, uniform in the interval -1, 1. Let's do that. And let me take a random variable that's clearly dependent. Let's say y is equal to x squared. So this is intuitively clearly dependent. Right. So in this case, what happens now? If y is equal to x squared, then okay, we'll show dependence also, that they are independent. But let's do exy. So what's exy? Okay, first of all, what's ex? Ex is just integral -∞ to infinity x f sub x at x dx, right? Now this is the same as, now x is uniform -1, 1, same as -1, 1 x times the density of uniform is the length of the interval, which is 2, 1/2 dx, right? And that is going to be equal to 0 because the function is symmetric, right? There's no problem. So ex is 0. So then I can compute ey, but I will not do ey. I'll do exy. Okay, exy is what now? Exy is same as ex cubed, right? And that's a simple exercise to just think that exy cubed is just ex cubed is same as integral 0 to 1 x cubed 1/2 dx, and that's again 0, right? Because it's an odd function. So let me put exercises there so you can just check it. Right. So now this will imply what? This will imply exy is equal to 0 is also equal to ex, which is 0, right? Which is same as ex times ey, because ex is 0, right? So therefore exy is equal to ex times ey. That's one. Let's call this as equation star. Right? So star holds, but clearly x and y are not dependent, because why? You look at the chance. Let's say look at a simple one. Let's say look at the chance that x is less than a quarter, right? And let's say y is less than a quarter, right? So what does this mean? This means that if you look at it carefully, it's the same as the chance that x is less than a quarter and x squared is less than a quarter. So that's the same as x is less than a quarter and x squared less than a quarter, if you think a little bit, so you need x to be smaller than a quarter, you need the square also. That means you want x to be between minus, let's say minus a half, because x squared is less than a quarter, less than x is less than a quarter. This is what you need. And this we know from a standard calculation. It's a simple exercise. Using density of x, you can get it to be equal to 1/8. Okay. This is because you just write it as a integral from minus 1/2 to 1/4 of 1/2 dx, and that's exactly equal to this. It's not hard to do. Very nice. Now at the same time, you go look at the other one. Look at probability x less than equal to a quarter times probability y less than equal to a quarter. Right. Now that's the same as what? That's the same as like above, probability x less than equal to a quarter, and probability y less than equal to x is same as x squared less than equal to a quarter. That's same as minus 1/2 less than x less than a quarter, less than a half. So this is a simple exercise. Again, you could calculate. I will not do this. In the same density function, you can write this as, let's say I write this down, the same as minus 1 to a quarter of 1/2 dx, and this is minus 1/2 to plus 1/2 dx, and that, if you do the calculation properly, you will get is equal to I think 3/16. So clearly probability x less than a quarter, let me copy this down, probability x less than a quarter, paste it here, is clearly not equal to probability x less than equal to quarter times and y less than. So joint probability is not the same as the product probabilities. So in this part, we know that the covariance is 0. So this implies that, let's put this in orange, this or pink, let's say. So this implies, this 2 in star implies covariance of xy is 0. Right? And let's call this double star. Call this double star. So just to make the note a little bit cogent on one space, let me make it a little bit smaller so that you can all see the whole thing in one page. So first I start an example where EXY is this. So X is uniform, and then let me do this computation a little bit. Sorry about that. A second. Make it a little bit smaller. Here, and then move this across here, the star. Right? So this implies that covariance of XY is 0. Make it a little bigger. I'll write again. And this part we can make again a little bit smaller, this calculation, that this whole thing. Make it a little bit smaller. Very cool. So I'll make this L moves across here. This, and then let's say it's also pink. So what does pink say? Pink says covariance of XY is 0, right? Pink says covariance is 0, and double star says covariance, they are independent. Right? So what does the example tell you? The example tells you that, so from star will imply that covariance of XY is 0, and then from double star we know that X and Y are not independent. So the converse is not true. So let me just make it double so you can just check it once more. Let me just go back. Let me make this double so you can see the whole argument like I did before. So let me go back up here. Let me get this thing down again. So let me go back up. Let's see, come back up here. Right, very good. So what we've done so far is the first part we showed that if X and Y are independent, then the covariance of X and Y are 0, right? In the second part, what we did was I showed you that if they're dependent, then also you can have covariance to be 0 as well. So the converse is not true. So independence implies covariance is 0, but covariance 0 does not imply independence because they're not. The example shows independence. Okay. So converse is not true. So let me just write this down so it's clear. So Oh, sorry, what's happening here? Very good. So what have we shown by the example? So the example shows that, example implies that covariance xy is equal to 0 does not imply x and y are independent. So the converse of the statement is not true. X and y are independent. Very good. Independent. Very nice. So now this is one we have seen several measures of understanding of covariance. It measures some sort of dependency. If they're independent, then the covariance has to be 0. If they're dependent, then it doesn't necessarily mean covariance continually. But covariance is large means that they're very, 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 very dependent. Covariance is small means the dependency is small. So now I just want to remove this one notion of correlation, which everybody uses a lot. So I'll write this down. So correlation, essentially what it does is it removes the units in x and y. That's all correlation does. So let me write this down. So correlation of xy. This is defined typically as rho. So rho is called the correlation of xy. Let me write this down. Correlation called core of x comma y. That's how it's called. So rho of x comma y, or rho is defined as the covariance of x comma y divided by divided by the standard deviation of x and standard deviation of y. So divided by the square root of the variance of x and variance of y. So what happened here? It came out well. Variance of x. Let me copy this and paste again, and I get variance of y. Covariance. So here what I've done is I have just normalized my covariance of x comma y. So notice covariance of x comma y has variance in terms of square of the units of x and y, because it's ex ey times. And this one has, I'm taking the units of x and the units of y. So multiply the two things out, I get no unit. So this is independent of unit. This measurement is independent of units. So this measurement is independent of units. Okay. And this also one can show, which I will not show today, but you can think about it. It's fairly easy to show, is that you can show that the correlation is always between -1 and 1. Okay. So that's one thing you can show. It's a number of -1 and 1, and it's independent of units. So it's a measure of dependencies of association between x and y. Right? And it's sort of dimensionless scaling of the covariance, and it's frequently used as an absolute measure of trends between x and y. So let's write these things down. So what I want to say, I wanted to say that this is so it's independent of units, I've said. So so first thing observe, this is something you have to show, something I will not show. The second point is the following: it has no units, that we have already seen. So you can think of it as rho is sort of the dimensionless scaling of the covariance. So I'm scaling the covariance by two quantities, standard deviation x, standard deviation y, to make it, it's a dimensional scaling, and it's frequently used. It's used as an absolute measure of trends. So that's an absolute measure of trends between x and y, between x and y. Okay, one must just be careful. correlation is just it's just one indicator. So there's something called causality. So if correlation is high, does it mean that does correlation imply causality? That's a very interesting statistical subject which I will not go into in this class. But so if correlation high doesn't really mean that there's a causal relationship between x and y. But so one last point I'll conclude is the following: if rho is equal to 1, that corresponds to the case when y is just absolutely equal to x. What happens when rho is equal to -1? That corresponds to the case when y is equal to -x. From the formula you can just check that, not hard to check. And the last thing, of course, we can say, we know that this fact is true, that if y is independent of x, then we know that the covariance is 0 at the top, so rho will be 0. So rho will be 0. So rho will be 0. So this implication is true, but we've already seen that this implication is not true. Okay, it's not true. Right? So this part typically in statistics is called as uncorrelated random variables. So they're not dependent, they're not independent, but they're uncorrelated. So independence means you're uncorrelated, but uncorrelated means you're not independent. Very cool.